Oh, welcome everyone to the Grand Rapids Public Museum. As you encountered coming on the way up here, there's a lot going on here, which is a good thing. You know, it's good to have a city that's busy. For those of you who don't know, my name is Chris Miller. I'm the president of the Grand Rapids Amateur Astronomical Association. Moving on to this particular presentation, which is called the Marron Memorial Presentation, and it's in honor of Jim Marron. And who was Jim Marron? Well, he was he came in the mid-1960s to the area, and he and his wife, Evelyn, and they had purchased a 16-acre tract of land that's a couple miles southeast of Lowell. And at the same time, the Grand Rapids Amateur Astronomical Association was still using temporary locations for their observing sessions, and they were looking for a permanent location. And Jim was on this committee that was examining alternatives, and they eventually reached the conclusion of, well, why don't you take a portion of our land and use that? Which we accepted and have been using that property for the last 52 years for that. And actually 52 is only since the agreement. They actually started construction a few years before that. So Jim was instrumental in allowing us to build the James C. Veen Observatory, and Jim was also a frequent visitor and user of the facility for the next 50 years. And we only recently, and then back in 2015, we did actually arrange to purchase the land on which we are. And so we now have 12 acres that is dedicated, that is owned by the association. And speaking of solar eclipses, little fact, that Jim Marron was able to view 8 of them. I've only been able to view 1 so far, so I'm hoping, I'll get 2 in with the 2024 eclipse, but I don't think I'm ever going to get to 8 by the time, unless I start doing a lot of traveling. Anyway, so the other avocation of Jim Marron was community theater, and he was active in the Grand Rapids Civic Theater and at the Lowell Community Theater. So he passed away in March of 2018 at the age of 87. Anyway, so in honor of Jim, we have this annual event to present a special speaker for us. And so with that, I will turn it over to Tom Good, who will introduce Dr. Bergin.
Good evening, everyone. It's a privilege to be able to introduce our speaker tonight. Ted Bergin is a professor in the Department of Astronomy at the University of Michigan. He got his BS in astronomy and astrophysics from Villanova University in 1989. He received his PhD in astrophysics from the University of Massachusetts in 1995. After a stint at the Harvard-Smithsonian Center for Astrophysics, he joined the faculty at the U of M in 2003. In 2008, he was the recipient of the Henry Russell Award, which is the U of M's highest honor for junior faculty. It recognizes extraordinary accomplishment in scholarly research, creativity, and excellence in teaching. In 2019, he was awarded the prestigious Heinemann Prize for Astrophysics by the American Astronomical Society and the American Institute of Physics for pioneering work in astrochemistry and innovative contributions to the physics and chemistry of star and planet formation, and for his tireless efforts to improve diversity and inclusion in astronomy. And I could tell you more about his work, but that would be wandering into what's it called? I'd be stealing his thunder. So let's give a warm Grand Rapids welcome to Dr. Ted Bergin.
Thanks a lot. It's a super pleasure to be here, and I'm going to have a little bit of fun here and talk to you a little bit about how we make that, and how common that might be. So what I do is I study the origins of stars and planets and try to understand how Earth-like worlds come to be and how they get their materials. And so I'll show you a little bit about how we do that today. You know, I grew up in the 80s, and this was my favorite comic book. I'm not going to read it. You could read it there. So that's Calvin and Hobbes. And so, you know, where did what I showed you come from? Our living planet, right? And is life preordained, and are we alone? And, you know, we live in an amazing time because we are at the cusp of beginning the journey to determine if we are alone in the universe. And that's insanely exciting. Okay, so I don't know the answer. I don't. However, we detected actually 5,000 planets over more than 3,000 systems. None of these are Earths. That is, an Earth-like planet at the same distance around a star like our sun. Why is that? Because the techniques that we use to detect those planets are not yet capable of finding Earth-like, exact Earth-like analogs. However, we have detected some planets that are Earth-like sized around smaller type stars that might potentially have life around them. We also have Jupiters parked right next to the star, which was a total surprise. And the most abundant type, or the most common type of planet out there, apparently are worlds that are like 1 to 2 times the size of the Earth. So these would be called, we call them super Earths or mini Neptunes, depending upon whether they have a gaseous envelope or not, which we actually don't know in many cases. All right, and what I do is we observe planetary systems in formation and are trying to understand the outcomes, okay? And as I will show you, we will begin the search for life, okay? So there's different kinds of focuses for life, and you know, one is how did life originate? I'm not going to talk about how, you know, abiotic chemistry became reproductive chemistry that we call biology. That's not my thing. But rather, I'm going to try and understand what are the conditions that foster life and how common are they, all right? And so what are those conditions? Well, one, it has to be a rocky world, and by that, it's not a Jupiter planet, right? It has to be the right distance from the star such that water, if it is present, would be liquid on its surface, as opposed to in the vapor phase or the gaseous state. So life, the solvent of life is liquid water, okay? And another important point, and this often is overlooked in astronomy, is the planet has to have a stable climate. That is, it has to have a climate that such that liquid water can persist on the surface for millions, if not billions of years, right? It took about 4-point-something billion years for complex life. Well, let's see, life originated 3.9 billion years ago, as best as we could tell. The oldest organisms we see, we think, are of order of 3.9 billion years old. Okay, complex life started about 3-point-something billion years later. All right? So over that time, billions of years, the Earth had a stable climate and allowed for that life to foster. So let's look at planet formation and the elements of life. So all life on Earth uses water as the liquid medium. All life on Earth uses one molecule to store energy in the cell. This is the ATP, or adenosine triphosphate. All life on Earth uses DNA as the basis for what I call chemistry with memory. This points back to a single common origin for life, okay? That all life, something worked, and it stuck with it, okay? So we can foster this. You know, what can do this? You have to have somehow the right elements in the right amount. So what are those elements? Well, this is us. And by mass, we are mostly oxygen and 18% carbon. The hydrogen and the oxygen are paired together, actually. That's H2O. all right, and then nitrogen. So these are the most abundant, actually, reactive elements in the universe. So hydrogen is the most abundant element. Helium is next. Helium is unreactive. And so the most abundant elements are what we are made of. Okay, that's a data point. What is the Earth made of? The Earth is made of something different. We know this. You could pick it up. It's the rocks. What are the rocks? The rocks are primarily silicate minerals, and they're mostly made of elemental silicon. And there's an awful lot of oxygen there as well. That oxygen is not from water. That oxygen is because oxygen is a main component, a primary component of silicates. And then there's a bunch of other things, okay? But this is what the Earth is made of. So these two things are different, right? What life is made of and what the Earth is made of are different. So how did that come to be? And what is that, okay? So what we can do is we can try to find the main carriers of hydrogen, oxygen, carbon, and even silicon throughout all the stages of planetary birth. All right? We could even track things in ices or the gaseous state. I'll show you most things that I'll show you will be detections of things in the gases. So the terrestrial worlds are made of the solids. These would be the rocks and ices. The gas giants are mostly made of the gas. All right? For us, for astronomy, and the data that I will show you, including data from the James Webb Telescope, it's easier to characterize the composition of the gas. But the neat thing is if we can determine the amount that's present in the system, we know the cosmic abundance of elements. So if I determine that 50% of the carbon is in the gas, I know that 50% is in the solid state. So you can actually determine things directly. And of course, the Earth is, if I want to understand how an Earth-like world is, I have to pay attention a lot to the solids. So this is a cartoon of star and planet formation, but I'm going to show you the actual images that show that this is actually right. So we have what we call clouds. The clouds are primarily composed of molecules. Something causes them to collapse, and it's a rotating collapse, such that as the thing gets denser, it's rotating, and in a rotating collapse, it collapses down to a disk. Now, why is that? Well, if I were to take my shoe off, as I do this in class, and spin it over my head, I can't spin it directly on top of my head, right? There's not enough centrifugal force for that to happen. And so that's why all that stuff on the poles in a rotating collapse goes right down to the center and forms that pancake, which is a disk, and the planets are born in that disk. All right, so I may use these things, I may not, but I always just throw them up there just in case. Astronomy is bonkers. The distance of the Earth to the Sun is 10 to the 11 kilometers. We call that 1 astronomical unit. 1 parsec is 3 by 10 to the 16th kilometers, 206.265 AUs. Light years I don't use ever, usually. The distance to the nearest star-forming region where we can actually see things is 125 parsecs, 300 light years away, 125 times 10 to the 11 kilometers, bonkers, right? I might present temperatures in Celsius. I probably will. 0 degrees Celsius is water freezing. So, this is an example of a region in interstellar space where at first when you take a picture, it looks like a picture of nothing. All right? But when we look at it at different wavelengths of light, so this is a picture at visible wavelengths, and this is where we look at another part of the spectrum of light. So if you think of the rainbow, the red part of the rainbow of light, that's the longer wavelengths. If I go just a little bit beyond that to what we call the infrared, if I look at that object, all of a sudden I'm peering through it. And you can see this rich star backfield behind it. And these things are painted red, or the stars appear red when we take the picture. What's happening is there's material in this object. And some of that material is actually tiny little particulate matter, about 1/10 of a micron in size, smaller than the width of a human hair. All right, and that is absorbing that starlight. That's what's blocking that starlight. That material, the solids, are made of silicates. And those are the seeds of terrestrial planets. All right, so this is our evidence, and there's other evidence beyond this, that where the Earth comes from. Now, we're made of other things, and one of those is water. And molecules in space, we can detect their emissions via, they actually rotate, and you're seeing the water molecule, the Mickey Mouse rotating, right? And also water can vibrate. It can do the funky chicken. It can do all kinds of things, right? And when these molecules have these motions, they are quantized, actually, the laws of quantum mechanics. And so there's only certain rotational states that are allowed, that is, rotational energies, if you will. And when a molecule gets excited, basically it bangs into something else, it gets some energy, it goes into an excited state, it spins more. And then, like anything, it likes to hang out, on the couch, eat some popcorn, the low energy state. It emits a photon of light when it slows down. That photon of light is at a specific part of the frequency or in the spectrum of light, such that I can take my telescope and I can go directly to that frequency or that wavelength, and I know that I am observing water. So that's what we do. So where in the spectrum of light? This is the spectrum of light. Okay, from radio, microwave, submillimeter, infrared. This is what we see with our eyes. There's ultraviolet, X-rays, gamma rays. We're familiar with this one, right? This is heat. Okay, and microwaves. We know what that is. Well, molecules emit mostly in the microwave and the radio, so we use these really big radio telescopes. This is the IREM 30-meter telescope in Pico Valletta, Spain. Very good food in the middle of nowhere. And, of course, there's this beastie that's in the infrared. And this is a telescope operating at wavelengths, if I go back here, it's right here in what we call the mid-infrared. Okay, and molecules emit at both of these wavelengths. So if I go back to this thing, which I did, is I used the IRM telescope to look for molecules, and there it is. That object is filled with stuff. I can add up the mass of material there. There's about 4 solar masses, 4 suns. The efficiency of star birth is about 20%, 25%. You're going to make one star like our sun, or maybe a binary system when this thing collapses. Now, this thing is 2 by 10 to the 12th miles in size. It's going to collapse down to something that's 800,000 miles in size. And that's equivalent to taking the great state of Pennsylvania, where I was born, and squashing it down to this, but no, this door here. All right, so it's already insane, but that's what it is. So now, if we look at regions where stars are being born, there's lots of these dark patches here. That's because material's gotten concentrated so that there's enough of those solids to absorb starlight. So the general interstellar space in the galaxy doesn't have many of these particles, but when you collect them together, they can start absorbing the starlight. So this is when we look at it at visible wavelengths with our eyes. And then if we look at the same region at infrared wavelengths where you're seeing heat, so this is conservation of energy that you're looking at. Those solids are absorbing starlight, okay? They're heating up, and when they do, they emit light. And that light comes out as heat or infrared. And so that's why you see a counterexample where it's dark, it's bright. And then there's these things here that are not apparent there. Those are baby stars. They're about 1 million years old. Stars, of course, live for billions of years, so these are really baby stars. When baby stars are born, they accrete matter. And there's a disk on their equator, and conservation of angular momentum says if stuff's coming in, I have to somehow conserve that angular momentum, so it accretes some onto the star, and it throws some other parts out. And so this is a James Webb telescope image. The star is hidden in here in a cocoon of dust, and it's ejecting material along the poles, essentially. It can't do it along the equator. And it's being collimated by the magnetic field of the star, and you can see lots of little knots. And this is really crazy, right? It's just gorgeous. And then as it gets older, it becomes less collimated, and the material that's getting out gets sent out on a wider angle wind. So this is, again, another baby star. This star is probably about 300,000 years old. There's a disk of material right here. This is where the planets are going to be born in this thing. They're not being born yet. And then this is everything that's coming off in this spectacular hourglass type display. So this is a picture of star formation, okay, and planet formation. That is, we have something collapses down to a greater concentration. We can look at it with different telescopes. This is with the Atacama telescope in Chile, where we can actually see the disks themselves. So what you're looking at here is the grains in this thing have grown. So when I tell you that the Earth is made of the silicates, those micron-sized particles collide together, grow, 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 grow. They grow until about a centimeter in size. And that's what we're looking at in this disk. You're seeing basically millimeter and centimeter sized particles that have absorbed starlight, and they're re-emitting it, and they're betraying a shape of this pancake. And these gaps here, we think, are caused by hidden planets, where things have grown beyond centimeter sizes. Okay? And there's a picture of another disk. This one's in molecules. And then I love this one. This is another solar system that you're observing the planets orbiting their star. I mean, oh my God, right? You know, when I started out in astronomy, I never thought I'd see that. Okay, so this is the constellation of Orion. And if I look at the constellation of Orion with carbon monoxide eyes, that is, eyes that could detect the light from a rotating carbon monoxide molecule, it's at 3 millimeters wavelength is where it emits, radio telescopes, you'd see this. All right, this object is about 100 light years in size. It's huge. Okay, it's mostly made of molecules, mostly molecular hydrogen. So it's mostly made of hydrogen. We call this a giant molecular cloud. We're very, to the point. It's really big, and it's made of molecules. Okay, so it's a giant molecular cloud. It's very cold. We can measure the temperatures of these objects, 10 degrees above absolute zero, negative 206 degrees Fahrenheit, and has enough material to make 100,000 suns. This is where stars are being born. Okay, this thing is made probably 10 to the 5th stars. What's going on there is, well, what is resisting collapse, there's a bunch of things, but one of them is gas pressure. Gas pressure depends upon the amount of stuff that's there. It also depends on the temperature. These things are really cold. They're 10 degrees above no temperature. So they're the coldest regions in the galaxy and where material is, and that's why stars are being born there. Okay, so now this is my favorite picture of Orion from an amateur astronomer. I used to look out my window and see Orion in the winter. There's Betelgeuse. This is an interesting spot here. This is the Orion Nebula. And if you look at that with one of the telescopes from the European Southern Observatory, you'd see all these stars here in this wispy material, okay? All these stars are baby stars. There's about 10,000 stars being born in this cluster. I'm going to look at this one right here, and what we did is we pointed the Herschel Space Telescope at that. That's a young star. That's a few 100,000 years old as opposed to these stars, which are a few million years. That star is still surrounded by the cocoon of its natal material, and that betrays the composition of the material that's there because it's really hot, and that leads to the molecules being very emissive. And so this is what a spectrum looks like. This is the transmission through the atmosphere. Herschel was a space-based observatory. This is frequency. This is emission. We're not going to worry about it. Every little line coming up here is a molecule screaming, hey, I'm here. That molecule right there is methanol. All right? And we can take this and we can basically take molecules in a lab and say, well, where are they going to emit and how strongly will they emit? And we can match this, and by matching this, we determine how much they are. What is their abundance? How much oxygen are they carrying? How much carbon are they carrying? How much water is present? And you can see this little light blue here, that's methyl cyanide. Somewhere in here there's ethanol. Here we go. That's alcohol. There's more alcohol in space than a million to a bajillion liters of alcohol are out there in space. Very hard to get to, but nonetheless it's there. Lots of molecules. The chemistry of interstellar space that precedes the birth of planets is organic chemistry. It's the chemistry of carbon, just like us. Yeah?
I noticed that some of the notation is you can actually identify isotopic composition.
Oh God, yes. Oh yeah. Yeah. So we can observe. So for example, oxygen has 17 oxygen and 18 oxygen. We can detect down to 18 oxygen. Carbon, we could do carbon 13, no problem. We can do 17 oxygen as well. And this actually turns out to be very important for us. It's an important tool. All right, so when we look at everything and understand where things are, we can figure out that most of the silicon is in this tiny particulate matter. All right? And that's going to make the Earth, basically. And oxygen, about 40% of it is locked up in silicates, and the rest of it's mostly in water, which is interesting. And the carbon and nitrogen is trapped along in water in sort of small organics and other things. So, I mean, it's interesting, right? The chemistry of interstellar space builds small organics. The chemistry of life builds really big ones. But when my students ask me, or when we think about whether silicon also has 4 bonds similar to carbon, and could you get silicon-based life, I think the initial conditions say no. There's no free silicon running around. It's all in the rocks from the beginning. From literally the beginning. The galaxy. So planet formation works like this. You have tiny little things, these centimeter-sized bodies. Some magic happens. We actually don't know what that is. And you get to planetesimals. And then, this is really cool. And you get to Mars-sized bodies not by planetesimals banging into each other, but by these planetesimals eating lots of pebbles, because it's a heck of a lot easier and they can grab more mass. It's amazing. In any event, then you make Mars-sized embryos, and then these Mars-sized embryos bang together and make an Earth. So here we are. Right? I've constructed an Earth. Right? What I have is those solids. Those solids have silicates, a water ice coating with some carbon on it. Right? So if you're going to think I'm going to make this planet, I'm going to make a planet that's got silicates, water, and some carbon. Hey, we got it. Right? So here we are. This is our water world. No, this is not a water world. This is a silicate rock with a tiny amount of water. We are less than 0.1% water by mass, our planet. It's fascinating. So what we think, that is, okay? So if we're in that disk out of which planets are being made, the sun is here, further away. It's hotter close to the star. It's colder further away. So at some point here, water had to be in the vapor phase, and then it was cold enough for it to freeze out as ices. So the way you could get a water-poor world, such as the Earth, is to form it inside what's called the ice line. We have a problem then, because there's no water there. We'll have to talk about that. All right, and indeed, when we point James Webb at planet-forming disks, this is a spectrum. Now, again, that's emission and wavelength, and each of those little lines is a molecule waving at you saying hi. All right, and we see things like hydrogen cyanide, carbon dioxide, and all the lines here, basically if there's a line going up, that's water. When we look at a young planet-forming disk, this is emission from water molecules coming basically at an Earth-Sun distance, okay? And all the water's in the vapor phase. So we sort of verify that assumption, that there's hot regions close to the star, which is like, duh, right? I mean, yes, there's hot regions close to the star. The water is going to be in the gaseous state, but we can see it. So that's cool. All right, carbon. And same story for nitrogen. Carbon-based living planet. All that green on the surface. We have a sprinkling of carbon. All right, if you look at how much carbon was available at one astronomical unit where the Earth was born, we got 1 carbon atom per 10,000 available. Yikes, right? Less than 1 nitrogen atom per 100,000 available. We are a carbon-poor planet with very little water, but we're here, right? So that's something, right? That's telling us something. That maybe that's what's needed, is not too much. I don't know. We're going to have to find out. All right, so we are a silicate rock with a tiny amount of carbon, oxygen, and throw in some water. And indeed, when we look at some disks with James Webb, what we see is an explosion of carbon. All right, so why is that? What I'm getting at is if we are a carbon-poor planet, right, if the carbon is not in the solids, the carbon has to be in the gas. So we should see it. And I've been trying to do that for 10 years now. And in some instances we can. And so that's what's happening here. This is a carbon explosion. This is what's benzene. It's the very simplest aromatic molecule. And this is acetylene. This huge thing is just telling us there's tons of carbon in the gas in that system. So again, saying that worlds that are going to form in that system are going to be carbon poor, like the Earth is, and water poor. So now we have a little problem. All right, I can make my planet, no problem. The silicates inside of this water ice line are carbon poor, water poor, plenty of silicates. I can make a silicate rock. How the heck do I get some water and carbon? Now, this is one idea, and the best idea that's floating around right now. There's others. And that is, it's what's called supply. And that is, when we look at the star here and things orbiting each other, they might have a gravitational interaction which will change the orbit of something. And what you're looking at here is the orbit becomes more eccentric. All right, so I get, from a near perfect circle to an ellipse. And that orbit will mean that that body may have other interactions and may be accreted elsewhere. It can also change the inclination of the body. Most things are orbiting in the disk around the star, and that gravitational interaction could also excite the inclination. And why am I doing that? Is because models of terrestrial planet formation, so if we take a sea of planetesimals here, and we're going to just let them interact and see if we can make bigger things, and you're going to look at inclination and eccentricity, and when it gets higher, that means there was an interaction, okay? And then bodies are going to start forming, and they're color-coded from where they originated. So out here, there's more water, actually, and there's less water here. And when they see a planetesimals, things are getting bigger here. But what's not happening is what I need to do is all my water is out here, and I need to move it here. So that's a problem. So one way to do that is to have a Jupiter. And so if I have a Jupiter here, okay, it actually excites things much more quickly. That is, gravitational interactions stir up that young planetesimal disk, and those planetesimals are able to bang together. And the other thing that happens is some of this stuff out here that's now coded blue, there's lots of water in this thing, get pushed inwards. And what happened there is that there's this idea that Jupiter moved, that Jupiter could have moved in and out, which is it's called the grand tack, after a sail tack. And so Jupiter moving in, for example, pushed a lot of stuff here. And all of a sudden we have stuff, this is 1 AU now, that's 2 AU, 3 AU, so that's the Earth. The Earth would have started here red. Now whatever bodies are starting to form there, they're a little bit more green. They got some water. And there's also carbon out there. So that's the prevailing idea. And I show this because the movies are kind of cool, right? But that's the idea. That is, you could form the Earth dry with very little carbon, And then if you have Jupiter present, it can just stir up things so that you might get some supply from beyond the water ice line, and that gives us what we need. Another possibility is that things just happen to form earlier when some phase where the water was still present. So we're working at it. Now, there's an interesting factoid that, okay, if, and this is an if, but if having Jupiter in the system matters, we actually have the statistics on how many Jupiters are out there now at Jovian distances, and it's only 5 to 10% of star systems have a Jupiter at that distance. If that matters for life, then that's a problem, right? It's a limiting factor, but there's tons of stars, right? So 10% is still a big number by that sense. But it might be that having a Jupiter really matters, and since some don't, this may titrate the amount of carbon, nitrogen, oxygen. We don't know yet, but it's where we are. So okay, that's getting the materials of life to a planet. All right, and we can think of ways to do it, but it may not be all that efficient all the time. The other thing that happened is in the context, right, when I was thinking about what a planet needs, it has to form in the right place, and the right place is what's called the habitable zone. All right, so this is what we call a habitable world. A habitable world is an interesting construct. It just says, is the planet at the right distance from the star if liquid water were to be present? If. We actually don't know whether liquid water is present on most of the planets that we've looked at. Okay, so here we are. If we look in the solar system, our habitable zone is basically the Earth to Mars. All right, Venus might have been in the habitable zone when the sun was young, but it's no longer in the habitable zone. So again, that's just it's the Goldilocks zone. It's where the temperatures are just right. And this is a very useful concept for astronomy, because when we look for exoplanets, one of the easiest things we can determine is the distance from the star. And we know an awful lot about stars, so we can actually tell whether a planet is in the habitable zone or not. Doesn't say that life is present, right? It doesn't say that liquid water is present, but if it were present, if water was present, it would be as a liquid and perhaps life could exist. So right now, when we look at the 5,000 planets, only 50 to 100 of those are in the habitable zone. Now, the planet must have a stable climate is the other interesting one, and I include this one because this is, I think, important for us. If I look at these things, right, this terrestrial planet, particularly this one, this is Earth and Venus, right? They're the same damn size. Venus is covered in clouds, 450 degrees Fahrenheit on the surface, rains sulfuric acid, lost all of its water, and we're a paradise that has lots of political problems. What happened, right? Why are we so different? And one reason is the way the Earth operates. And it's linked to what's called the greenhouse effect. And the greenhouse effect is something you actually are all familiar with. It's called climate change. All right? And it's just a planet. It's not crazy. It's not a planet. So what happens, why the Earth is not a freezing ball of ice in space is because we have an atmosphere. And the atmosphere warms the surface. Visible light from the sun goes through it on a non-cloudy day. Now we're in Michigan, but okay. There's non-cloudy days. It gets heat absorbed by the surface, and even on a cloudy day, some of the light gets down, absorbed by the surface, and gets re-emitted as infrared light. Molecules have motions and energy states at infrared wavelengths. That James Webb spectra that I showed you of all those water lines, that's water that could absorb heat. There's energy states that, so what happens is gases like water, CO2, and methane in the atmosphere absorb that light. Most of the atmosphere is N2. That doesn't absorb anything. O2 also doesn't absorb anything. Why? Because they're homonuclear molecules. They have two identical atoms, so they don't respond to the infrared light. The other molecules have some asymmetry, so they do. So that's molecular physics. So they absorb that light. Some of that light gets emitted out, but some of it gets emitted down. That's trapping heat. And of course, climate change, what's happening is we're adding more CO2 to the atmosphere and increasing the efficiency of this. Okay, the other thing then, okay, so if we look at the Earth and Venus and Mars, okay, here's Venus and the Earth and Mars. This is the average surface temperatures. Okay, if you have a no greenhouse temperature, look at those temperatures. We all would be frozen balls of rock in space. But Venus is insane. Okay, and why is that? That is because most likely all the carbon that Venus was gifted at birth is in its atmosphere right now, which is not true for the Earth. What the Earth does, okay, if we had all the carbon that's on our planet in the atmosphere, we would be like Venus, but we're not. That's because the CO2 is dissolved in water. There's 60 times more carbon dioxide in the water, oceans, and 3,000 times more than in the oceans locked up in rocks. All of our carbon is in the rocks. And what's doing that is two things. One is oceans, and the other is plate tectonics. That is, the oceans suck up the CO2. The CO2 in the oceans reacts with basically limestone minerals and makes things like carbonates that sink to the bottom, and they get subducted back deeper down in the Earth via plate tectonics. And of course, we know that the Earth is split up into plates, and where these plates are banging together is where there's lots of earthquakes and such, right? But what's happening is you have material gushing out in the middle of the ocean, but then there's the continental plates right here where the ocean is getting pushed, and it's called subduction. It's getting pushed underneath here. This is the plate for the continent, and the ocean plate is getting pushed down. So that's taking some of that carbon and sticking it deeper in the planet. Venus doesn't have oceans. It was too hot. The water went into the atmosphere. Plate tectonics may have started there, but once the oceans were gone, it stopped this process from happening. And the CO2 cycles back here, right, through these ocean vents or other volcanoes. Okay? So Venus was too close to the sun, lost its oceans. It doesn't have what we call the CO2 cycle, and it's a dead planet. Okay? So for other Earths, the distance from the star is important. The amount of carbon and water may be critical. We don't know. There's some planets might get more, some planets might get less. It's possible if you get more, you would have a stronger greenhouse, but we don't know. It depends upon if plate tectonics is present. Regardless, I'm guessing that Venus might be the most common type of exoplanet, rocky type of exoplanet that's out there. So now, are we alone? Last little thing. So there's a problem with looking at planets and looking for life, and that is a star is 1 billion times brighter than the planet. Okay? And the way to think about this is, so there's that lighthouse and that fly, and that's in Los Angeles, and I'm in Washington, D.C., and I have to detect the fly. Okay? That's what we are doing, which is kind of amazing when we detect exoplanets. Okay? And so what we'll be looking for are what we call biosignatures, and that is when we take the spectrum, and I showed you spectra, so I showed you, all that explosion of things going up, right? Well, planets are warm, and their light passes through the gases. So instead of things going up in that diagram, they actually go the other way, down here. So this is the Earth, the temperature of the Earth, and then these are the molecules in the atmosphere of the Earth absorbing the light. This is the greenhouse effect, basically. Okay. So this is intensity, wavelength. There's the Earth's emission. This is heat. The Earth is basically 300 Kelvin, give or take. Okay, it has ozone in the atmosphere. That comes from O2. O2 is the molecule of life, right? It was created by life. It says photosynthesis happened. So if we could detect this at another planet, boom, New York Times. We have life. We're going to argue about it, astronomers, but we're still going to say that life is likely present. Another feature, methane, cows releasing gases, is present. That's also due to life. So these are what we call the biomolecules, and the pairing of methane and oxygen. So these are just different wavelengths, okay? So methane is down here. It's a tiny little thing. These two things don't like each other, okay? They don't want to be together. They're reactive. This is going to make something like CO, okay? The only way oxygen and ozone and methane are in the atmosphere of any planet is if they're being continually produced. There has to be a source term. And on the Earth, we know what that source term is. It's us. Actually, it's not us. It's tiny little microbes, right? But in any event, if you look at Venus and Mars here, they have CO2 in their atmospheres, but nothing else. You can actually see a little water at Mars at some wavelengths, but I guess we don't see it in this one. But Venus is all CO2, and the Earth has things like ozone. Nitrous oxide, that's another one that's a potential biosignature. So we are going to be looking for this over the next 30 years or so. And this is one of the best spectra of an exoplanet that James Webb has obtained to date. This is of an 8 Earth mass body, so it has a big hydrogen envelope. So James Webb is going to try to get down to Earth masses. It's actually not sensitive enough. Boo hiss, $13 billion, and you still can't do it. But this is amazing. When I saw this spectrum, so this is the data, the points here, and then the red here, the blue is a model. And the data goes down when the model says it go down in the presence of methane in the atmosphere of that body. So, what are we going to be doing? Well, NASA has a plan to build a much more expensive telescope than the James Webb Telescope called the Habitable Worlds Observatory. And if we could build that, it's going to take 20 years. I will not be an astronomer at that point. That will have as its goal to be able to detect life around an Earth-like planet. Concurrently, there's 3 big telescopes being planned on the surface of the planet. So one is a 40-meter telescope built by the Europeans in Chile. The University of Michigan has partnered at some level with this one. And then there's the Giant Magellan Telescope. This will be a 23-meter telescope. That one is in the process of being built. We're waiting for the United States government to decide whether it wants to do anything, and it may take a while. And the same with this one. This is a 30-meter telescope. These are the 2 American concepts. This one's being built. These hope to be built. These 4 things will be searching for whether we are alone in the universe. This one within 4 years, these probably within the decade, and this one. This is going to be the big one. So, to end, I'll end with this. This is from Arthur C. Clarke. Either we are alone in the universe or we are not. And no matter how you slice it or dice it, that's either terrifying. So, thank you very much. I'll be happy to take any questions that you have.
Yes, okay, good. I just want to start with a question. This isn't so much about surface or atmospheric chemistry, but how important is a magnetic field?
Right. So from the perspective of life, cosmic rays or energetic particles, so these are energetic particles that are launched by stars. In particular, our sun launches particles which is called the solar wind. And those energetic particles can be damaging for life. And the Earth has a strong magnetic field that deflects those particles. And we think that a magnetic field may be a prerequisite for life to have that protection. There are some extinction episodes back in the history of the planet that may have been related to when the field reversed. So the magnetic field in the Earth, for reasons that we don't understand, reverses in polarity, and there's a period where it goes to zero. If that were to happen when humans are around, I'm a little worried about that. But right now I'm worried about other things. In any event, magnetic field, yes, important. So we are trying to detect, basically, that there can be energetic interactions between particles and magnetic fields, the ones that are close to the star, that could emit at things like X-ray wavelengths and things like that. So people are looking for these towards, like, say, hot Jupiters. Really massive things, lots of envelopes, must have a magnetic field right next to the star. And so the answer is we are trying. We'll never be able to tell if an Earth-like world has a magnetic field.
On the slide for planet formation, you mentioned that there's a mystery or a controversy for moving up from the millimeter to centimeter sized up to the planetesimals.
Right.
What's the controversy?
Right. So it's what it is. It's not really the current theory is something that's called the streaming instability. So the dynamicists have all these instabilities where things will happen. And what that is if you can get enough dust, we call the solids dust, concentrated in a certain area, in a basically an annulus, then this instability can kick in and you can immediately make planetesimals within 100,000 years, 1,000 years. That is the best theory we have. The question is, how do we test it? And we're working on that. And so, the key thing about science is when you have ideas, they have to be testable. And that's what we're trying to do, is test that theory. Okay? Yeah.
Well, thank you.
Yeah.
All right. As the son of James Marron, I was thinking about demonstrating my intelligence by identifying the Bach globules, the Herbert-Haro objects, or even talking about phosphorylation, otherwise known as the Krebs cycle.
Sure.
But instead, I think I could teach you how to find Earth-sized objects using the data you have already.
Okay.
Now, if a planet transits in front of the star, after it has made third contact, the magnetotail, our geomagnetic tail as an example, has taken samples of the atmosphere, which includes the dust, the salts, the atmospheric compositions, and it becomes an absorption lines in front of the star. Mm-hmm. And you could tell a great deal about the orbital characteristics, its magnetic field, and its compositions, even if it has an atmosphere.
It's not, that material is not dense enough to present an absorption feature that is detectable with our instruments. There are some planets that are lava worlds, and if they are, they must be emitting material that may be trailing them, and that might be detectable.
It's the trailing material of the magnetotail.
Yeah,
and they have already used this to discover the atmospheric components of a Jupiter, super Jupiter, that transits a star that starts HD and a six-digit number I can't remember.
Sure.
My question, back to the thing about being able to identify isotopic compositions, is can measuring the proportions of isotopic composition of particular elements give clues as to further detail that you would not be able to deduce if it was just telling you what elements the chemistry alone?
Sure. So one of the things I try to do is ask what role does formation have to play in the ultimate composition of a planet? Okay. And I can observe the gases. Gas giants are made of the gases. Okay. So in principle, when I observe the composition of a disk, I would hope to see it reflected in the planet. And if I don't, then that's telling me something perhaps about the evolution of the planet, or maybe it's telling about something about how the planet formed, and it's different from what I thought it was. Okay? There are some planets that have been detected that have an excess of elemental 13 carbon. So the isotopic ratio in interstellar space is for every one 13 carbon, there's 70 12 carbons. That's basically from stars dying and throwing their stuff out into space. Averages out. Okay? This planet has a ratio of about 25 or so. So it has more 13 carbon. How did that come to be? Well, I actually know how it came to be. There's chemistry that happens at below 35 Kelvin. That's 35 degrees above absolute zero. So that's the minus 400 and something degrees Celsius, okay? That can lead to an excess of 13 carbon. And so that chemistry must be operative sometime before that planet was born. And can I see it? And the answer is we're beginning to see it. So yes, there are ways to use the isotopes. And I could talk about deuterium. The Earth has an excess of deuterium in its oceans, okay? That excess, we know where that came to be. That excess requires chemistry operative below 30 degrees above absolute zero. So this water first formed at that temperature. When did that temperature happen? My student and I wrote a paper about it about a few 100,000 years before the sun was born. Okay, and we can tell that from the isotopes.
Hello. Thank you very much. It's been a fascinating presentation. I was wondering if this material is available for us to review or other material that you might send regarding.
So most of this, I think this is being taped, right? I can make the slides available for
Slides
sure.
would be great if that's
Yeah.
available. Thanks.
I'm just curious, within your field, if you could snap your fingers and have the answer to one question, what would it be?
Oh man. You know, there's a war, right? Because I want to know, are we alone in the universe? Okay, but I really am trying to figure out how the Earth got its carbon, and I have a theory out there that I think is right. I'd like to know if it was right, but I think I'd have to go, are we alone in the universe? Yeah.
Hey, yeah, thanks again for being here. This was a really nice presentation. During the presentation, you mentioned that you think Venus is the most likely outcome of terrestrial planets or rocky planets. Was that specifically for planets with an atmosphere, or do you think Mercury's are particularly uncommon compared even to Venus's?
Right, so Mercury has an excess of iron.
Okay.
It's much more denser than any of the other planets. That forms so close to the sun that maybe that's the answer for why it is. You know, the why I think Venus is because I actually think, you know, there's this idea I have with carbon is I think that there's probably a zone in the disk that is very strongly carbon rich. And if you form a planet there, it will have much more carbon than the Earth has.
Okay.
All right, and under that circumstance, without plate tectonics, that would be Venus.
Cool.
It would lead to Venus.
Gotcha. Thank you.
Yes, thank you again. I'm just curious, and I'm very much a novice, but I'm very curious about this whole new NASA mission, the Psyche, I believe, sending something out to orbit an asteroid.
So OSIRIS-REx, you mean?
Yes, is that it? The recent launch from a couple weeks ago where they're going to
Yeah, where it landed. Yeah, sure.
And I guess I'm hearing on NPR talk about how, reviewing this will help kind of maybe determine how an Earth-sized core is developed. Tuesday, okay. Well, the launch that was last week.
That was Psyche. That was Psyche.
Yeah, so
Okay.
I guess the question, Brian, I was just curious your thoughts about this mission, Psyche, because
Sure,
we're talking about
sure,
habitable
sure,
planets,
sure,
and I guess
sure.
there's this mission that just got launched that years from now
Right.
they'll reach it to determine what about this asteroid in the core that could potentially be tied to
So
how Earth was formed.
the Earth's core, we know, is iron and nickel rich. There is a light element in the core of the Earth. That is, the density of the Earth's core is slightly less than that of iron and nickel. That light element could be anything from hydrogen to silicon. I don't think of silicon as a light element. I'm an astronomer. Hydrogen is a light element. But okay, these are Earth scientists. So for Earth scientists, anywhere from hydrogen. One element, it could be carbon, for example. Most of the carbon in the Earth, if there's carbon in the core, that's where most of the carbon in the planet is, which is pretty fascinating. So you can go to Psyche, which is in a stripped out core of some larger body, and maybe that would reveal to you what the composition of the Earth's core is, and then what are the geophysics that led to the formation of that core, and maybe I can understand for example, what the light element in the Earth's core is, or other factors. Okay?
Are you familiar with the discovery that at the bottom of the continents may be trillions of tons of diamonds?
Yeah, I heard something about it, but yeah, so there could be...
This is why our continents are floating.
There are people, I mean, there's lots, I listen to what the geophysicists say, but when you look at the accounting, if there's carbon in the core, that's where most of the carbon on the Earth would be. And we do have some ways of estimating how much carbon is deep down in the mantle, but if it's locked up in diamonds, maybe you couldn't access it. So I don't know. Yeah.
I'm wondering what role, if any, does radio astronomy play in finding life elsewhere in the universe?
So I'm a radio astronomer, and what we are doing is, one is this, okay? So if you want to understand where water came from, water emits at sub-millimeter wavelengths and also infrared wavelengths, okay? So that's radio astronomy. We are able to look in those disks that I showed you one picture of. We have many pictures of those things. Then we can measure the motions to meter per second precision. And we're looking for hidden planets. Based upon if the planet is present, it will induce a velocity signature that we might see. And so that's one thing that we're doing with planet formation. So number one is the composition. That's the big thing. Okay? Molecules. And let me see, dust, the dust growth. Right? If you want to study dust growth, you're doing that at radio as well.
Okay. Another thing, in one of the earlier slides, you showed images of protostars where you could see the disk and the plumes erupting from the poles. What would we see if one of those plumes from the poles were pointed straight at us from that distance?
Right. So it's obviously they're easier to find when they have big angle on the sky. Okay, and when they're pointed right at us, they're harder to find. Okay, so that's one statement. But what would we see is the motion that we can measure is using what we call the Doppler effect. Okay, and if something is pointing right at us, the Doppler effect is at a maximum, and we would tell that thing is present by the way it would affect how light wave is emitted from that source. Yes, you got it.
Are there any research projects underway or nearing completion that you're keeping an eye on?
Hundreds. The Atacama Array and James Webb are amazing, and we're able to do things. I tell my students this is the first time anybody's seen this in the history of humanity. Every one of those spectra, okay? And so every one of those things is just a gold mine. And so I'm tracking, how many of those spectra show that signature of excess carbon in the gas. That's what I want to know. We're looking at water. There's systems that have lots of water, some that don't have that much water. Well, where is the water? It must be in the solids. Why? Okay. There's ways that material can move in the disk that could change the composition of planets that are born in it, even when the gas is there. So stuff can move around. So you might get elemental enhancements in certain spots. I'm tracking that. And then I'm looking at any exoplanet spectrum where they can get compositional measurement.
It's my understanding that astronomy is one of the fields in which amateurs can make significant contributions. Do you know whether or not radio astronomy is making contributions through amateurs doing the kind of thing that you are doing?
Yeah, so these facilities are, anyone can apply, but by and large, it's just the practitioners that are using them. Where, in the domain of radio astronomy, where amateurs are getting involved is in SETI. So that is when you're listening for ET. So SETI obtains a lot of data that they can't reduce. And so people can dedicate their computer CPU to reduce SETI data. And so that's an area where radio astronomy and amateur astronomy are melding together. I went to Green Bank, yeah, a couple times. Before it collapsed? After that one collapsed, yeah.
So just curious of the sensitive equipment that's out there right now with the James Webb and whatnot, and the other one's being built.
Can
How-
you
hear
say
me?
it?
Oh, I just wondered, how do they calibrate that equipment
Oh,
and
okay.
aliasing, preventing aliasing effects when you take your measurements? Is there a method that works like that?
Yeah, there's so many different calibrations. They have to calibrate the wavelength axis. They have to calibrate the flux axis. For the total flux, we look at asteroids. So we know what the flux that we expect the asteroid to be. We observe it, and does our instrument recover what we expect? Okay, and so that's what we're doing. You use asteroids, and sometimes you use quasars as well, but for the most part, I think they're using asteroids for James Webb. In radio astronomy, I used to use planets. Mars was a big one.
One more. Dr. Bergin has to drive back to Ann Arbor tonight, so let this be the last question.
There's this theory that I heard from another, astronomer on a vacation that I ran into, and it's been stuck in my head ever since. And I just want to know if it's something that you would dismiss out of hand or not, or if it's just another one of these untestable type things. But in the formation of planetesimals, she offered this theory that there's micro black holes that could possibly account for that suction, that these scientists are having a hard time explaining, observing, testing. Is this something that sounds like crackpot science, or is this something that's just okay, thank you. Yeah, I just wanted to, no, that's a very appreciated answer. Yeah, thanks.
Yeah, I don't think so.
Okay.
Very good. Well, let's thank Dr. Ted Bergin for his talk tonight. Thank you. Thank you. Thank you, and check in grAAA.org for all updates on our coming events. And if, for those of you who are not members who would like to investigate membership in the grAAA, you can do that online, or you can talk to any of the members here tonight. Thanks for coming out. Good night.